My name's Mark Alexander from the University of Cape Town, and I'm currently visiting at IITM Madras. And it's a great pleasure to be able to be with you this afternoon and to present this lecture. The title is The Developments in the Performance Approach for Durability and Service Life Prediction for Concrete Structures. I appreciate the opportunity to give this lecture because for me it's a great honor simply to be here in IITM and to be asked to give this lecture, so I appreciate that very much. Just a bit of background, that's the city where I live and work. It's called Cape Town. It's the most southwesterly tip of the continent of Africa, and it's a very beautiful city, as you can see. It has a waterfront. It has this iconic mountain called Table Mountain in the background, and that structure right in the front is the soccer stadium that was built to host the 2010 Soccer World Cup. The semi-final was played in that stadium, and so what you're looking at there is a picture of the city. But of course today we're in Chennai, and this is another iconic structure here in Chennai, the old Central Railway Station, a beautiful building. And this is a very interesting city as well. I've thoroughly enjoyed being here, and in particular we're at the Indian Institute of Technology, Madras, here in Chennai for this particular lecture. Okay, so that's enough by way of background. This is what I'd like to cover in my lecture today. An introduction, just setting the scene, then something around performance-based approaches for trying to achieve durability in concrete structures. That will allow us to move on to talking a little bit about service life prediction, and then I'm going to give you some practical examples drawn from our own experience and also some work that was done in Canada, and then briefly talk about what is happening about code approaches, developments in code approaches for service life, and then I'll bring the whole thing to a close at that stage. We know that concrete is the material of choice for infrastructure and construction worldwide. It's functional, it's efficient, it's universally available. There again in those pictures you can see on the left-hand side is that same soccer stadium that I showed you in the first picture under construction. On the top right there are some very elegant precast concrete panels that would be used in a high-end or high-tech application. And then on the bottom right, in fact, is just ordinary construction going on in a very rural or a very low-tech application. And that's the marvel of this material called concrete. It can be used in all kinds of applications, from the high-tech to the low-tech, and people can use it as a material that will help them to improve their lives. It's the developmental material par excellence. It's the material we use to develop our world in which we live. So here is an example of block construction, which is based on, of course, on cement. Here is in fact, a high-tech concrete road. This is a continuously reinforced concrete pavement built in our country, in South Africa, but being built with relatively low-tech methods. So it's a high-tech application built with low-tech methods. It's largely labor-based construction. So you can do high-tech construction even using labor-based kind of construction. You don't always need the very high-tech stuff. Here is an example of another application. This is one of the newer dams that we've recently built with roller compacted concrete. This is called the Brumhoek Dam, and it's part of a pumped storage scheme, electricity pumped storage scheme on one of our mountainous regions. It's a very beautiful structure as well. And these were the precast viaducts that were cast in segments in a huge precast factory at the time. It was one of the largest in the world. This was at the time that the high-speed rail link in Johannesburg and Pretoria was being built, in time, in fact, for the Soccer World Cup. So this is for a very high-tech application. Those were stitched together as viaducts for the high-speed train. So this is how we can use concrete in all kinds of applications and for all kinds of uses. Also, concrete is surprisingly a very green material. People think of it as not. But if you look at the figures there, you can see that concrete has relatively low environmental impact factors. Whether it's embodied energy or CO2 emissions, the figures look extremely good. The reason why, of course, we have an issue with this is because concrete is produced in such huge quantities. So if you have so much of it, even multiplying it by relatively low figures means in the end there is a large environmental impact, but not because the material itself is unfriendly, if you like, environmentally unfriendly. But having said that, we do know that we have problems, and the problems that we have are largely around what we call premature deterioration. The fact that concrete, on occasions, deteriorates more rapidly than we would like it to do. So we live with this problem of deteriorating infrastructure, sometimes collapsing infrastructure, sometimes infrastructure that does not fulfill the need for which it was designed, and so it comes to the end of its design life rather early, or its useful life, and that impacts on economic growth, it impacts on losses to the economy as well. And of course it uses up resources that we could well use elsewhere. So the key questions then that we need to ask are the following. How do we address concrete deterioration? That's largely what I'm going to be speaking about today. As engineers, as designers, as owners, there are a number of people involved in this whole picture. Then what are the approaches to ensure durability in concrete structures, particularly in aggressive environments? And then is it possible to attach a notional design life to a concrete structure, and if so, how much? And what do we mean by service life prediction? I'm going to explore some of those topics today. This is at a relatively high level. We're not going to get into a huge amount of detail. I'm trying to sketch a philosophical picture within which, or a framework within which we can understand these problems that I'm talking about. So with that as background, let me talk a little bit about performance-based approaches to durability design and specification. I'll try and help you understand what this means. In the absence of what we call performance-based approaches, the possibility of rational or engineering approaches to design, durability design and specification will elude us. We will not be able to do them. Performance-based approaches provide an integrated approach, allow us to have an integrated approach in which we use governing parameters, and I'll talk about some of those just now, in all kinds of different ways, in design formulation, in deterioration modeling, and then in specification and quality control on site. So you can see the big picture can emerge from this kind of thing. Also, in a performance-based approach, we have to consider deterioration mechanisms. We have to understand what deterioration is occurring, how it's occurring, and what rate at which it is occurring. And very importantly, if we do have what we call a performance-based approach, there must be verification of performance properties that influence durability. We have to be able to verify that we get what we hope we want to get. So that's a little bit of background. So the aspects that we consider then are quantification, very much so, quantification of the environment, in this case environmental loads and the dominant deterioration mechanisms. How can we quantify these things? They're very difficult actually to quantify. We need performance criteria. For example, what will be the end of service life criterion that we will use? Will it be a certain amount of let's say, corrosion occurring, a certain amount of cracking, a certain amount of discoloration, a certain amount of loss of surface of the structure, or whatever? How do we decide when the end of service life has been reached? We need prediction models, or really these are deterioration models to give us rates. We need the rate equations, and very importantly, we need ways of considering variability. Concrete is itself a variable material. It exists in a highly variable set of environmental circumstances. The weather, the environmental loads, they all differ all the time. The structure varies with time, and so variability is with us all the time. So we need to be thinking about probabilistic approaches and other possible ways. And then, as I've said, we need appropriate specifications and quality assurance systems to verify compliance, because that is the very essence of a performance approach, is the verification that you get the performance that you wish to have. And that brings me to the issue of how we do specify concrete for, in this case, particularly for durability. And there are two main types of specifications that we use in engineering. The one is the prescriptive approach. This is the common approach, the one that you will find just about everywhere throughout the world. This is the norm, if you like, at the present time. And the features of a prescriptive approach are that it sets certain limiting values for the concrete, mixed materials, mixed proportions, and things like that. It might prescribe construction processes, it may or may not, but often does, for example, how you should cure, how you should finish, and things like that. And it works on what we call a deemed to satisfy approach. So the specification says this water binder ratio, this minimum cement content, this minimum strength, or whatever, cure it this way, finish it off that way, and if you do all that, then the structure is deemed to satisfy the durability provisions. Of course, what does that mean? It means very little, because many of these things we cannot even check on site, and to have it deemed to satisfy a durability criterion when we've actually measured very little is really thinking it's what we call pie in the sky. It doesn't actually work. So there are many disadvantages related to a prescriptive approach. There is no in situ verification. We cannot guarantee the in situ properties, that they have met in fact up to the specified requirements. We cannot really control the quality of construction, not particularly well. There's absolutely no way that we can do service life prediction because we have nothing to model this on. There is no ability to model in this approach. It doesn't allow us to do proper economic analysis, cost analyses or maintenance budgeting, because we just don't know when things may go wrong or when we will reach the end of a certain type of condition, a deterioration condition. And of course it stifles innovation because it's just a set of rules. You know, obey the rules and then everybody will be happy. It doesn't quite work that way. So that is an approach that increasingly we're suggesting we should do without. We should put it where it belongs in the waste paper basket. However, the reality is it's with us today and it's going to take a long time before we finally manage to move properly away from this approach. And this is just an example that we have from our own work of this drawback of using prescriptive approaches. This is a set of data in which what we're plotting is oxygen permeability index, OPI, which you probably are mostly familiar with, on a log scale on the y-axis against compressive strength on the x-axis. Now, these were in situ measured properties. So what I'm saying is that the OPI we measured in situ on the actual structures that we were working with, and the compressive strength we measured in the lab on standard control specimens, okay, normally cured. So we've got all the influence of construction on the OPI, and we've got only the influence of standard curing on the compressive strength. And you can see that there is just no relationship whatsoever. Okay, you can kind of get any OPI value for any compressive strength, and it simply indicates that when you start to measure real in situ performance, which is what you can do with OPI, you find that you simply do not get any correlation with, say, strength. And engineers tend to use strength as the parameter by which they control everything else. If you do this work in the lab, you'll get very nice correlations. But go onto site, and this is exactly what happens. This is the problem of verification that I was speaking of earlier. Okay, so if we move away from prescriptive to a performance approach, where durability becomes what we call a material performance concept, then what we need are the following things. We need measurable performance criteria. How do we specify an actual performance criterion? Specification of performance limits. What limits will we work with? We need, of course, test methods. This is the big thing that we often do struggle with, test methods. Then we need performance limits, as I've said, to judge acceptable performance. These have to be derived not just from some sort of thumbsuck, but from proper models like service life modeling. Judgment can come in, of course. And in this way we can get what we call an integrated performance approach. Now, this was a diagram that in fact Somerville, way back in '97, which is, if my maths serves me correctly, 20 years ago, came up with. They were already thinking along these lines, and this is a good example. So we start with exposure conditions, and then we move from that through to performance-based design using mathematical models. We come up with performance specifications as output parameters, and then importantly, verify, verify, verify. You have tests to do that with, and then of course you have the feedback loop as well. So that was a very advanced thinking at that time, and we've moved beyond, or we've moved in this realm now considerably since then. But that's really what we're talking about. And here's another diagram maybe also to help us understand it. Here we have a whole lot of different people involved. We have the owner of the structure who has to outline the performance requirements. Then we have the engineer or the design consultants. They work with the structural design. Of course, they produce the specifications, which we're talking about. We then get the concrete producer, possibly a ready-mix producer in this case, who has to produce a material with the correct properties. And then the producer supplies it to the contractor, who executes it. And finally, what we want is a durable concrete structure. Notice that the durability has to occur in the final structure. It's not good enough to simply have a durable concrete coming out of the ready mix plant. You have to prove that you've got durability in the final structure. That's the critical key here. So we need a set of functional requirements here to ensure that all of these parties understand their roles and play their part effectively. So it requires a significant amount of coordination across the whole value chain, if you like, of the construction process, which of course prescriptive approaches don't require. Then there's this issue of performance testing. This is where we have struggled now for several decades to find reliable test methods for doing things like mix pre-qualification and then actually during construction the as-built quality of the structure itself. There's no shortage of tests, absolutely no shortage. RILAM has done a lot of work here. I have my RILAM shirt on today, by the way, and RILAM has done work through many technical committees, and that's really good work. But despite that, we still don't have internationally accepted test methods. Some have more or less achieved that status, but across the board we struggle to get test methods that actually give us what we want. And so this is a major challenge, because without the ability to test and verify in situ, we don't have a proper performance approach. Just a brief word on durability indicators or durability indexes. These are physical or chemical or sometimes electrochemical parameters that characterize concrete at the engineering level. So they are easily interpreted in an engineering context, and they're easily and reliably measured. And in fact, these things, these durability indicators, can be a great way forward in terms of moving into this performance setup. They need to be sensitive to all the things that will affect the final structure, the processing and the environmental factors, and they're a very powerful means to characterize the durability, the potential durability of concrete. The typical parameters may be things like permeability, conductivity, indirect maybe a porosity index or maybe some kind of chemical property. And the examples are given here. Resistivity is one that we often use now. We have different kind of chloride penetrability or chloride resistance tests, RCPT and so on. We have the oxygen permeability test, which is a very good indicator of carbonation resistance. And we might be things like calcium hydroxide residual, which will also influence things like carbonation. So there are a bunch of these things, but we haven't quite learned yet how to integrate them fully into performance approaches. That's a challenge that still remains. So let me try and summarize where we are at the moment about performance-based approaches. They're gaining acceptance, they promote innovation, because now you can start thinking rationally, you can start thinking how to actually do rational engineering design, doing things that engineers do best. They deal with concrete performance during the service life. We have to be able to verify that the structure has achieved what we wanted to achieve, and then we can do something about predicting service life. The as-built properties are specified prior to construction, but if we do not measure these performance requirements within the real structure, for example in relation to durability, then in my view these are not truly performance-based specifications. You can't simply do cube testing. And some approaches that you find in the literature, which are called performance approaches, in fact are not, in my view, because they do not go through to this final very important step of requiring as-built assessment. And that is always a trick. And I showed you some of those pictures, that picture of the OPI testing earlier, which was done on the actual structures. That is very important. And so the problem is it actually possible to assess in situ durability properties? And that's a huge challenge, which we are still grappling with today. This is what has largely held back the full implementation of a performance approach. So with that as background, we can talk a little bit about service life prediction. Service life prediction is a determination of the notional service life of a structure. How much life can we get out of this structure in terms of decades or years, whatever? So it's an attempt to quantify the useful life of a structure. Which implies then that we need to have adequate durability, so we need a durability limit state. We need serviceability limit states. We need verifiability, that's the problem, as we often come up against. And of course in all of this we should not approach the ultimate limit state. And engineers understand this question of limit states very well. So we can work with that. We can approach service life prediction either deterministically, in other words, simple models which give us single value kind of answers, or we can do probabilistic modeling. preference for the latter because of this huge variability issue that I spoke of earlier. And the problem is, of course, that we do not have many modern concrete structures with which we can actually verify that the approaches that we're using for service life prediction are going to work. So if somebody comes to me and says, I want a structure that will last 100 years, I don't have a problem. I say, I can do that for you, because I know I won't be around in 100 years to show that I managed to achieve it. So, you know, in a sense, it's a little bit it's a little bit esoteric. How can I actually guarantee 100 years when I cannot retain the responsibility for ensuring that I actually get that service life? Nevertheless, that is what people are asking us for these days. They say they want a 100-year service life, and then as engineers we have to try and do something to prove that we might actually get that. So there's a great need for studies on real structures in order to see whether the approaches that we're using are actually working. And this is, of course, difficult. This is hard work. It's easy to work in the lab. When you get it down to a real structure, it's always difficult, because there's the question of access, there's the question of responsibility, there's the question of safety, all kinds of things. Difficult to do there. The essential elements in service life prediction are this understanding of deterioration mechanisms. Are we dealing with sulfate attack? Are we dealing with reinforcement corrosion? Are we dealing with soft water attack or whatever? So we have to understand deterioration. And the ability to translate those deterioration mechanisms into some kind of rate equations, mathematical models that allow us to predict things. And then, as we've indicated, ways of actually measuring material parameters. These robust characterization and quality control tests, which have to be routinely carried out, easily carried out. We can't take 6 months to measure these things. We've got to be able to measure these within the space of hours or days at the most, because we use them in quality control. And quality control means that they want an answer tomorrow for the problem that they have today in terms of site construction. And I'll refer to a few of these later on, and of course many of you are familiar with some of these tests. There are a number of service life models out there in the open source software. So you get Duracrete, Duracon, Life 365. They all have merits. They all have demerits. They're all based on rate equations one way or the other, and they relate a performance to a quality control test. But the conformity criteria are still issues that we grapple with, because we have to calibrate these against known performance, and that means studying real structures. And I come back to this question of integrated scheme. Many of these are not properly integrated, where we use them for specification, some specification limits. We use them for quality control. Can we measure them on the real structure to prove that we get it? And then can we use them in prediction? And that's a nice scheme, because if we can use a parameter, let's say a durability indicator or a durability index, for each of those three purposes, then we have an integrated scheme. So for example, we specify a certain value, we find out on site that we didn't get that value, so then we can go back to our prediction model and say, okay, we didn't get what we wanted, so what will the effect be on the service life? How much less service life are we likely to get because we didn't get the performance we wanted? And then we can immediately start doing remediation. If necessary, we can put a coating on, we can put an extended a maintenance warranty or something like that in place. It allows us to act far more rationally. So really what we're saying is, can we move from the intention of the designer to the production of the concrete through to the quality and the final construction that we really want? How do we bridge the gap through that entire range of activities? And that's what a performance approach allows us to do. And what we really want to be able to do is to say, can we do service life prediction here, and can we do verification over here in some way or the other? That's the big picture. So let me then move. I've now really given you some of the philosophical and framework background to this whole problem of durability specification, service life modeling, performance approaches, and so on and so forth. Let me now deal with a couple of practical examples of these. And I'm going to deal with two. The approach that we have developed where I come from in South Africa, and then the Life 365 approach with some work done by Mike Thomas from New Brunswick in Canada. And by the way, these are some of the structures that we have studied in the approach that I will be showing you just now. That was some major freeway upgrades that we did some years ago, and we were able to actually be involved in the site construction very extensively to try and implement this approach. This is how the approach works in our setup. This is a framework which we have used for many years. And the important things here, I don't want to go through this in detail because there's a lot of stuff here, but importantly, we talk about material indexes or durability indexes, and I've just defined those. I'll briefly refer to them again. We talk about quality control, we talk about structural performance, we talk about prediction, and we try and tie all of these things together in some way or another through the approach that we're using. So for example, you see things here like correlations, there and there and there and so on. So there's a lot there, and importantly, one of the things that we really have found very, very helpful is to develop these things called durability indexes. Where they're defined here, they're a quantifiable engineering parameter that characterizes the concrete durability. In this case, what we call the potential durability. How potentially durable is this concrete? They are sensitive to all the things that influence concrete quality, the materials, the processing, the environmental factors, and they are based on the measurement of transport properties. And they can be carried out importantly either in the lab or in situ. And the two that I just want to show here, there's actually also a sorptivity test, and I know that they're in action here in your own laboratories, are the oxygen permeability test and the chloride test. In the case of, I'll come back to those now, but they are also linked to service life models. So here's the link between material parameter and prediction or service life modeling. And we have two initiation models, one for carbonation and one for chloride resistance, which account for material type and environment, and it is an integrated approach as I described earlier. We can use them in design, we can use them in specification, we can use them for quality control. And here's an example of the implementation. This is from that, I showed you those freeway structures earlier. That was part of what we call the Gauteng Freeway Improvement Project, which was rolled out by our South African National Roads Agency Limited, SANRAL. So this was a major piece of construction over a period of several years in that part of the country. And in this case, the criterion, because it was inland, not at the coast, the criterion was a oxygen permeability index in order to control carbonation resistance. In other words, our concern was reinforcement corrosion due to carbonation. And that was this is the specification. The contractors were required in situ to achieve concrete with an OPI of at least 9.7, in which case they got paid 100% for the concrete. If they achieved values that were less, they only got paid 80%, and below that they got paid, well, nothing at all. Now you will realize that with OPI, this is a large range. 8.75 to 9.7 is almost a factor of 10 because this is a log scale. So they were being quite lenient here, allowing the contractor to go quite far down and still giving them a reasonable payment. So that was a specification. You'll also notice that there were specifications around cover on the right, but I won't deal with that now because that's just as important, that you get the actual cover you specify. And this is just to show you how the model works. So for example, for a 9.7 OPI, at 100 years we would predict roughly 30 millimeters of carbonation. That's the model. It's deterministic, and I know that there's a lot of variability, but that's roughly how it works. That's the basis for the 9.7. If you only get 8.75, you can notice that you're going to get about 60 millimeters of carbonation in 100 years. And if you only have 30 millimeters of cover, then your service life is only going to be about 10 years before you get carbonation at the level of the steel. On the other hand, if you go up to really good values of around 10.2, which is this curve at the bottom, then of course you get a really very, very good service life. So that gives you the sensitivity to the parameters that we were measuring in situ on the real concrete. And this is what actually happened. We measured, we got data from 5 sub-projects. Actually we got from more than that, but I'll only report on the 5. And what you can see here is that the mean OPI in all cases exceeded 9.7 in this column here. And you can see the number of data points in the column called N. A lot of data points, and in every case we got at least the mean value. That's good. On the other hand, if you look at what we call the proportion of defectives, that wasn't so great. We got as high as 40% results not achieving the minimum, and in one case we got 0. So they achieved it in every case, with a whole lot in between. And if you look at that on a sort of a histogram basis, that just shows you what happens on site. This is a really good example of what happens on real construction sites. Basically the concrete going into these 5 sub-projects was all the same concrete, coming from more or less the same plant. However, the difference is the contractors, the actual execution that was given out in 5 separate contracts to 5 separate contractors. And this is what the contractors did with the same input material. This is what they did on site to the concrete, if you like. And so, of course, the best one was down here. And you can imagine that where that was produced. That was produced in an on-site precast plant to make median barrier walls. So when you do stuff in a precast operation, you can really get excellent quality. And here you can see, those are the 9.7 values. I haven't done them on every graph, but you can see that in this case there was a huge amount of underperformance. You can also see that here there's a huge spread of data. Here the data is much more well confined. So the variability is now actually being able to be quantified. So that was a really interesting example to us of whether we could achieve this on site. And you can on average, but very often you don't get it in every case. So that was the first example. The second one is from this work that Mike Thomas has done on service life prediction. He's using Life 365. I'm not going to go through all of this. This is chloride prediction. In the Life 365, really what it does is it allows you to determine the rate at which chlorides enter into the concrete. And so you have to do things like find the surface value of the chloride content. It assigns an apparent diffusion coefficient, and from there you can calculate using this kind of equation at the bottom of the slide exactly when the chlorides will be at a certain point within the structure. So that's what the model does. And then they had this site at Treat Island in Maine, where they have exposed concrete for long periods of time, and they looked at, in this case, at the performance of slag concrete and saw whether the measured chloride ingress that they were able to actually go and measure was in any way represented by the model. And, well, yes, it was pretty well. Here are concrete blocks after 25 years with no slag in them, and you can see that the model is predicting reasonably well. And then for slag concretes, you would expect a steeper profile, and there too the model was doing reasonably well. So these are very simplistic examples, but the model was not calibrated by this data. It was calibrated by other data. And of course, when you have a model that's calibrated by certain data and then you apply it to new data, that's the real test of a model. Can it work with data that has not been used in its own formulation? So that was interesting. So what can we say from this? We've had 2 examples here which shows that yes, we can make reasonable predictions for service life, at least deterministically. Probabilistically, that's still quite a challenge. We've used this in South Africa for as-built quality and variability, and in Life 365 you can do, to some degree, some kind of prediction for that. However, we need the long-term verification. Is this really working over the long period of time? That means we actually need to go out and study damage quantification and things like that. Very briefly then, to bring the lecture to a close, what about developments in code approaches? All of this stuff is very interesting, it's very exciting. As researchers, we love this kind of stuff. This is what gives us oxygen and helps us to get out of bed in the morning and gives us a smile on our face. What about code approaches? Engineers, they'll listen to what we've just said, but they'll say, well, what does that really mean? I work to a code. I work to a code of practice. That's what an engineer will say to you. So that's very important. And so if we're going to get practical application of what we do in research, we have to find it embedded, or make sure that it gets embedded in codes of practice, codification. And in that case, we need limit state criteria, we need defined service lives, we need these deterioration models, we need compliance tests, all the things I've in fact spoken of before, strategies for maintenance and repair, and also quality control systems. And there are different frameworks here. This is the framework that the FIB uses. It comes from the model code for service life design. They're working on this. There's a new code coming out in a few years. And here you can see that they have a number of different approaches to tackle this problem at the code level. In fact, there is the deemed to satisfy approach, which is still there, but there's the full probabilistic approach, there's the partial factor design, and sometimes if we have a real problem with deterioration of concrete, maybe we should just try and avoid it. So, use stainless steel reinforcement, not black steel, or coat the structure so completely that nothing can get in. That may be a valid approach if it's just a very small structure and a very highly sensitive structure. That might be something we should do, for example, for nuclear power stations, maybe, and so on. So it depends on which framework you want to follow. The problem is we're continually getting new materials, and that's where the prescriptive approach cannot handle this at all, because the prescriptive approach is based on past experience. So when you immediately get a new thing coming along, like LC3, how do you handle this? There is no past experience to go on, so the prescriptive approach completely shuts you out of applications. And here, so we need ways, but the performance approach can get us there, of course. And there are different ways of doing this. I won't go through this in detail, but in the European context, there's the European technical assessment that you can use in the interim before you get into the full code approach. Those sorts of things can be done. There's also the equivalent concrete performance concept, which is covered within the European approaches. Again, one can read this up if you like. What I'm saying is that all of these things are there from a performance approach perspective, without which we cannot even begin to think of how we actually use these new materials in real construction, because engineers want to know that these things will work. So let me bring this to a close. First of all, durability and service life predictions for concrete structures are needed. We are being required as engineers today by our clients, by the owners of infrastructure, to provide proper and quantifiable service life. Longevity, sustainability, all are coming in there. The current prescriptive approaches simply do not do the job, because we have all these new materials, new technologies. None of that can be handled within a prescriptive approach. We need to move to performance-based approaches. This is desirable, and indeed it's inevitable to address these challenges that I've tried to indicate today to you. And the code developments are absolutely essential if we're going to be able to roll this out into engineering practice. So there's a lot of work to be done, and enough for your lifetimes, I'm sure. So with that, I thank you. That is a 30-ton concrete dolos used for coastal protection on one of our new harbours, and you might just recognize the national flag. Nandri, thank you. Right, so I don't know if there's time for questions. The question is about the 5 sub-projects, and we saw the different variability and the different proportion of defectives that we were getting. We didn't manage to quantify that. All we know is that they were each let out to different contractors, but they received concrete from a central plant. So the concrete was the same, the specification was exactly the same, but it went to 5 different subcontractors, if you like, or contractors in sub-projects, and they each had structures to build under the big scheme. And so it simply indicated to us that different contractors had different ability to produce quality concrete. That their quality control that they had, the training of their labourers, the methods they used on site all clearly differed, and we were able to actually quantify that difference, at least at this level of the material, the quality of the material. But exactly, we couldn't dig and dive into everything. Of course, we were working a little bit remotely. We were getting the data from the sites and then processing it. We weren't ourselves physically involved on the sites. That would have been another study. Why did that contractor do better than another one? Of course, on the precast operation, that you can clearly understand there. There they got absolutely 0 defectives, which is just again a real example of how really excellent work can be done in a properly controlled environment, such as precast. Other questions? Yes.
When you have testing done at site and the concrete fails in terms of durability,
Yes.
and the structure has been constructed at least partially, what do you do?
Yes, that's the key question, isn't it? Well, you can pay them less to start with, and then you have some money in the bank to do something, say to coat the structure, or to give it additional, maybe if there is very inadequate cover, because the other part of this question is not just the quality of the cover, it's the quantity of the cover. I haven't spoken about that. But if your cover is very deficient, you can already put in sacrificial anodes, for example, or something like that. So that's one possibility. You can at least determine possible remedial work and decide whether this should be done now or in 10 years' time or whatever, and you can put in a proper maintenance scheme. Of course, in the worst possible case, you may say, well, please demolish and reconstruct. That never happened. May I just mention that this was very much an experiment. I mean, the agency, the National Roads Agency, were really very courageous, I think, very bold in coming in with this entirely new approach. And this is almost unheard of, that you find a national agency willing to go out on a limb, and I can assure you they took many bullets for that. People who said, you're crazy, you can't do this. Well, they said, we can do it, and they did. So they they sort of took an educational approach to this. They said, look, this is new. The contractors have never done this before. We're not going to be too tough. So they use this as an opportunity to help to train and educate the contractors into these new methods. And now it's become common practice within the agency to do this kind of stuff. So contractors have, and initially they were very resistant because they said, you know, this is yet another requirement that we have to fulfill. But once they learnt how to do it, some of them embraced it and did very well. So yeah, so in fact we've been talking to the agency about being a little bit tougher about, because sometimes I think they're a bit too lenient.
So you told about chlorides and carbonation, where limits for chlorides and carbonation and models based on them, where the governing factor is morely the transport property.
Yes.
So problems like sulfates, acids or ASR, where it's more of chemical effects. So what sort of limits can be implemented?
Well, that's an extremely good question. You can see that the main concern we had was reinforcement corrosion, because that accounts for the vast majority of the deterioration that we see in concrete structures. It's around corrosion. And you have a lot of corrosion work going on here for good reason. The other kinds of deterioration mechanisms, ASR, sulfate attack, soft water attack, whatever, would need their own similar approach philosophically, but you would need the test methods, you would need the criteria to judge, the limits that you would set. And there are performance tests here. You know, I mean, some of the sulfate testing is in a way performance testing, but how you relate that to the real structure is a big issue. And that is always the trick. That's always the challenge. Can we relate these to, you know, so sulfate testing has certain limits to it, but is that really what's happening in the structure? These are the challenges that we face. So this all needs developing, and if there was a particular criterion that you needed to set for a certain deterioration mechanism, you could do that. For example, that one dam that I showed you, that roller compacted dam, that is a pumped storage scheme. So they have a dam at a high level and a dam at a low level. That was the low level dam. They pump water up during periods of peak of excess electricity to the high level dam, and then during periods of peak demand they let that water out of the high level dam through very large tunnels, about 3-meter diameter penstock tunnels, through the turbines to generate power for a couple of hours at a time. Now those tunnels were lined in concrete, and we were asked to look at a deterioration mechanism for, and that would be soft water attack. So we did work on the soft water problem for that particular application. Yes.
For different same concrete to different contractors, there was variability. Do you think it is because of the nature of the work that has been carried out in situ? For example, if it is a small tank or a small residential house that has been built to a site where a lot of public usage has been, like for example it is a main freeway or something. So because of the importance of the project, that would be the variability, or
in this case, bear in mind that this was all to do with freeway construction. This was the same kind of construction. Every contractor had so many bridges to build and so many culverts to build and so many median barrier walls to build, etc., etc. So this was all much the same construction. There was not variability in the type of structure being built in this case. They were all bridges, and they were all within the same area, using the same basic source of concrete and materials and so on. So this, I think, is a reflection of their construction practices. How well they're compacting the concrete, how quickly they strip the concrete, whether they then protect it properly, the degree of curing that they're carrying out and for how long, and things like that. So I think it was a reflection of their of how good they were doing, how well they were doing their construction. That's all I can put it down to. And that then further reflects on equipment, plant, training, understanding of processes, commitment to quality, all these kinds of things come in there.
Well, thank you very much, Mark. It's always
Thank
a
you.
pleasure talking to you and have you visit us.
Thank you very
Thank
much.
you.
It's been a great pleasure. Thank you.